Good morning, everybody. Happy New Year to all of you. I hope you switched well into 2024, and I hope it's going to be a less disturbing year. All right. Look, if you look at the board and you do some archaeology, there are leftovers from our last session before Christmas. What does it say? Slowly rotating sphere. Well, this is one of the applications we had with the tensor virial theorem, but I do not want to go into any detail there again. I want to switch to a new chapter today about stellar dynamics, but before we do that, let me come to two organizational matters. You've seen a survey that you may have seen a survey that I started on our website here. And this has to do with your participation in the final exam. And when I looked this morning, there were 43 of you who wanted to participate. Let's see. There are more. Okay. You see, I just had no idea how many of you wanted to participate. And you means you being present and all the others being not present and watching the stream or the video and so on. So I wasn't sure how many of you would like to participate in the final exam, and now you see there are 48. This survey will remain open until Wednesday after the lecture. And then I know a room of what size we are going to need, and I'm still targeting for the exam one of the lecture times in the exam week between February 5 and 9. Let's see if that works out. I mean, we need to find a room that is big enough, or two rooms whose sum is big enough, I don't know. All right, so that's the survey. If you haven't participated, and if you want to give me your opinion, please fill that in. Okay, then at 10 o'clock today, there will be a quiz opened about plasma physics and magnetohydrodynamics, and there will be a quarter of an hour for that. And well, when the time comes, I would like you to participate in that quiz for me to see where you stand, and also for you to see what typical questions I would like to have addressed with this part of the lecture. Okay, so far so good. Do you have any questions so far about, for example, the exam? Please don't ask anything. There's nothing I can say yet, but maybe you have some worries. Yes?
Is there a way we can take the other two quizzes again?
Yes, there is. Yes, there is. You want me to switch them open again?
Still for practice.
For practicing? Okay, I think that's a good idea. Yes, I'm going to do that. If I don't, remind me of it. Okay, very good. Then let's come to this chapter of the lecture. And I have to say, in all previous renditions of this lecture, I didn't have time enough to talk about stellar dynamics, just because I talked so much about other things. I thought this is not good, because there are many aspects of stellar dynamics that we should talk about. Similarities, differences to the other chapters that we talked about before, and also, since stellar dynamics is so important for understanding many things in astrophysics, and you hear terms from stellar dynamics everywhere, such as the Jeans equation, relaxation times, gravitational relaxation times, the Coulomb logarithm, Chandrasekhar's dynamical friction formula, and all these things, right? You should at least have an idea of what this is about. And so I thought, okay, let's rush a little bit with the other chapters. Let's squeeze them a bit and leave some time for stellar dynamics. And this is what I would like now to enter into. And this means that we are entering into chapter 5 of that book. Yeah, and see how far we get in the little remaining time of this term. Okay. This is not good for writing on the board. Okay, let's get into that now. Good. What's the problem? The problem is that we want to make sense of the motions of stars and galaxies, or of the motion of galaxies and galaxy clusters, for example. So we observe some things and we want to conclude about other things. What do we see? Well, first of all, we see a light distribution, for example, in a galaxy, or we see a light distribution in a galaxy cluster. In other words, we see some kind of projected density. What else can we see? We can take spectra, and we can observe spectral lines, and we can compare the position of these spectral lines with where they should be, where quantum mechanics tells us where they should be. Now, how do you know? You see a spectral line. How do you know what element this is from? Of course you don't, right? So you have to look for specific patterns in a spectrum, such as the very, very characteristic sodium doublet. This is what makes the street lamps orange. A very, very characteristic doublet line. Or you look for a magnesium triplet, and also a very characteristic feature. In other words, you search for characteristic features in the spectrum, and by their shape recognize them, and by their position you can then say something about the motion. By the Doppler effect you can say something about the motion of the stars whose spectrum you're taking. So what you see is some kind of dynamical information and some kind of positional information. Now what do you want to know? Well, I don't know what you want to know, but a common problem in astrophysics is that you want to infer what is the mass distribution like. Very simple question, very difficult to address. All right, so the question is, how is the visible information related to, for example, the underlying gravitational potential or the underlying mass density distribution of some object? That's the point. That's what we want to find out. Okay, now what's the problem? The problem is that you can't shield gravity. Maybe you have tried at home. I'm sure you did not succeed. The problem is, in comparison to electrodynamics, even though the Coulomb force also has infinite range, like gravity, there's just one gravitational charge, the mass, one type of gravitational charge. And therefore you can't shield anything. Remember what we did in plasma physics, right? We saw that rearrangement of charges of different type leads to a shielding of the Coulomb potential and leads to an effective Yukawa shape of the former Coulomb potential. And the Yukawa potential has finite range, and the problem is gone. So that means if you are sufficiently far away from a charge that you place artificially into a plasma, or more realistically from a charge fluctuation that you may have in a plasma, you don't see that anymore. And that makes the situation much more stable than if you cannot shield the interaction. Now have a look at at gravity. Let me just start with an example. The example is very simple or simplistic, but it will illustrate something. Suppose you have a disk of stars, right? A disk of point masses, and suppose this has infinite extent. I told you it's a simplistic example, okay? Now you focus on one particular star, and since you have assumed, no, I have assumed, an infinite extent of that disk, it doesn't matter which star you pick. Okay, so here we have it. And now we draw circles around that. 2 of them. So here's our star. It has mass m, like all the other stars we are assuming. And now we draw 2 circles about it. Perfect circles, as you see. And we ask, what is the gravitational force exerted by all these stars in a ring about our fiducial star? Okay, so gm squared over r squared is the absolute value of the gravitational force between any 2 stars. Now, how many stars do I have in a ring of width rdr? I have 2 pi rdr, that's the area of an infinitesimally thin ring, times number density small n of the stars. And here you see the problem, right? This is gm square n divided by r dr. So if I integrate this from some radius r1 to some radius r2, you see that this goes like gm square n ln r2 divided by r1. And as you go to infinity, the gravitational force becomes infinitely large. Of course, this is wrong, right? Because gravity has a direction, and if you have a truly random field of stars, there cannot be a net gravitational force. Right? Because if it's truly random, then you have no preferred direction, and then the gravitational pull has no direction to pull into. But this is a warning, right? This is a warning that clearly shows, since the gravitational force falls off like 1 over r squared and cannot be shielded, if you add more and more stars by going to larger and larger distance in a stellar distribution, you add gravitational force inevitably. And this is not the case with the electromagnetic interaction, right? Because of shielding. Okay, so you cannot shield gravity, and this gives rise to a massive problem. And of course, if we want to do this correctly here, we need not to look at the gravitational force itself, because its expectation value will be 0 in a random field of stars, but at fluctuations in the gravitational field. Right? We will have to see, as we extend the distribution of stars towards infinity, do these fluctuations die out, or do they just pile up? Okay. Let's have a look at that. So let me write down here. Fluctuations are the problem, right? Even in a random stellar field. Okay, now let's have a look at the following situation. Suppose I have a star here that comes along with a velocity v and now encounters other stars, such as in this disk here. Here is one. Now it's going to be deflected. It's going to be accelerated by a gravitational force exerted by this other star. Now let me calculate the change of the velocity of that star in Born's approximation. In other words, what am I going to do? I am going to evaluate now the gravitational force between these 2 stars along a straight trajectory. In other words, as I am evaluating the accelerating force between these 2 stars here, I am assuming that one of the stars remains at rest and the other one flies at constant speed. So I'm neglecting the change of trajectory while I am evaluating the force that changes the trajectory. That's Born's approximation. Okay, what's that gravitational force? Well, this is then the perpendicular, well, if I do it like that, then I can neglect the part of the gravitational force that acts parallel to the trajectory. Because it will be the same in magnitude, but the different in sign, while the star is approaching and while the star is moving away. So the net acceleration of this star by that star, parallel to the assumed unperturbed trajectory, is going to cancel out. So I don't need to care about this. And another way of saying this is, since I'm assuming Born's approximation anyway, of course the velocity along the assumed trajectory is not allowed to change. Okay, good. So what I need is, let's take the absolute value of the perpendicular force. And this is going to be the perpendicular gradient of the gravitational potential. I know there's a minus sign, but since we take the absolute value, okay. Good. So now I'm introducing a perpendicular coordinate b. I don't know who came up with the idea of calling the impact parameter b, because it's not the impact parameter. Okay. So this is going to be the absolute value of dB. Now, gm square divided by, okay, let's call the other coordinate along the particle trajectory x squared plus b squared. And this is what I have to take the absolute value of. And x has its assumed 0 here, so that I can write x equals v times t, and if t is 0, we have the moment of closest approach. Okay? Good. Now, what is this? This is gm squared b divided by square root v squared t squared plus b squared, and the square root to the third power. Sorry, this is not a b here, this is v. Okay, that's the accelerating force. If this is the potential energy, then I have an m square here. If this is the potential, then I would have an m here. What I need is a change of velocity. So I need f perpendicular divided by m. Then I need to have the perpendicular gradient of the potential. And I have this, okay? Good. Now, if I want to know the complete change of velocity, I need to integrate now this result over all times. Okay? So then we have the change of the perpendicular velocity. And of course, by our assumption, the parallel velocity is not going to change. So this is going to be gmb. Now the integral from minus infinity to plus infinity over dt square root v squared t squared plus b squared to the third power. Okay. Well, now it makes sense to, first of all, pull the impact parameter out of the square root here, which will be a factor of 1 over b cubed. and then to introduce as an integration variable tau equals Vt divided by b. Now if I pull b square out of that square root, what remains is v squared t squared over b squared, which I introduce as the square of a new variable tau. And then the Jacobian of this transformation is b over v. And now I can integrate Now let me integrate from 0 to infinity and take this twice. Okay? Now, it's interesting to think about how you actually solve this. I know you go to Mathematica and you ask it, and then it tells you what comes out. Nonetheless, it's interesting to see how you would do this by hand. I'm not going to do this now, because Mathematica tells you that this is 1. No more, no less, just 1. Okay. That's the overall change of that velocity. Now let's do the following thing. This is the change of velocity of the star that we have focused on by an encounter with a single other star. Of course, we have many of them. So let me ask now, what is the total change in delta V square? Right? Because we saw if we just add up the gravitational force, its expectation value is going to be 0. The interesting part is its fluctuation. But for the fluctuation, I will have to calculate the variance or the mean square of the velocity change. Okay. So this is this expression here for a single encounter. But now I will have to multiply with the number of encounters. The number of encounters, let me take a two-dimensional distribution of stars again. So within the impact parameter B and an infinitesimal width dB of the impact parameter, I'm going to find that many stars. Okay, and now of course, let me call this capital delta V here. Now of course, this will the complete change, or the complete squared velocity change, is going to be the integral from some minimal impact parameter to some radius r, which could characterize the stellar system. Okay, we can't set this to 0 because we have assumed Born's approximation. If I had 0 impact parameter, certainly Born's approximation would be wrong. So how do I have to set this minimal impact parameter? I'm going to set it in the following way. I know that delta V perpendicular is 2gm over bv. So this means that the relative change delta V perpendicular divided by V is going to be 2gm divided by bv squared. And I want this to be less than 1, which is certainly a crude way of estimating how long the Born approximation will be good. Nonetheless, it gives me a limit, namely b is larger or equal 2gm over v squared, and I call this the minimum impact parameter. That's a crude way of estimating, right? But we do not need any more than that right now. Okay, now, of course, you do see the same problem as before. Let me just calculate this. So this is going to be 4 times 2 is 8. 8 pi g square m square times n. I'm just collecting expressions that do not change under the integral. And now again, I have an integral over b db divided by b squared. So that's an ln of b. That's an ln of r divided by b min here. This is the first version of what I called the Coulomb logarithm before, often abbreviated as ln lambda. This is very often used as an expression for I don't know what to put in here. Right? Because what exactly would we write down for the radius of the stellar system? Do we really trust this estimate for b min? Right? So the Coulomb logarithm is often used as a bin for throwing things into that you don't really know. And then you give it a number and you say, my friend calculated this with a computer. All right. Okay. Now let's see. Now we need some estimate relating the radius to the other properties of our stellar system. And we can use the virial theorem for that and say, okay, generally we will have mv squared over 2, that's the kinetic energy of a single star, that will be of order 1/2 gm squared over r. Virial theorem. Right? Now here I have to take the overall mass of the stellar system, which I now call capital M. Then the mass of a single star cancels out, and I'm going to use that the total mass is given by r squared pi times n times m. Right? The complete radius of the stellar system squared times the number density times the mass of a single star. Okay, so then you see v squared is approximately g r pi n m. Or the radius is approximately v squared divided by g pi nm. Sorry, let me do this a little bit differently. let's, instead of writing the mass in this way, just say the total mass, the total number of stars, capital N divided by M. That's going to be a bit more smooth then. Then we have GNM divided by R, and we have R equals V squared divided by GNM. Okay, let's do it like that. And then you see that the ratio of R and the minimum impact parameter is going to be V squared divided by GNM, that's R. B min is V squared divided by, divided by 2. I'm sorry. Yes. Good. Now. All right. So you see we have this ratio here, and this just turns out to be, since everything else cancels, n divided by 2. That's the Coulomb logarithm, or the log of that is the Coulomb logarithm. Okay, now let us return to our formula here, this one, for the absolute change in the squared velocity. So then you see delta V perpendicular squared, that's 8 pi g square m square n divided by v square ln capital N over 2. But now you see g square m square divided by v square. That's related to the radius. So how do we do that? Gm g square m squared divided by v to the 4th power this is r squared divided by n squared, right? According to this expression here. Okay, so I can write this as 8 pi. Now I have g square m squared divided by v squared. So that's this expression times v squared. So this is r squared divided by n squared v square n ln n over 2. Okay, good. So the next thing you see is that the relative change of the velocity here is just given by 8 pi r square n divided by n square ln n over 2. But now you have pi r square times n. Right? Pi r squared times n, that's the complete area covered by our stellar system, times the number density n, that is the complete number of stars. Right? So this is just 8 divided by n ln n over 2. Okay. So this just depends on the number of stars we have in total. And you see that the change is the larger the number of stars is. But now, this is the complete change in the perpendicular velocity of a star, or in the overall velocity of the star, according to our Born approximation. But in a single crossing of the star through the stellar system, right? Because we have integrated here one encounter of the star in focus with one other star, and then integrated over all other stars. But it's one crossing of the stellar system by our fiducial star. So then, if I want to know what is the complete change after a certain number of crossings of the star through a certain number of crossings of the star through the stellar system, I just need to multiply this by the number of crossings that I do have in a certain time. So that's going to be the number of crossings times 8 over n ln n over 2. And now the number of crossings within a certain time t so if I have a time t available, then I can cross the entire stellar system in a time t that is given by 2 times the radius divided by the velocity of the velocity of the star. Let me call this delta t, that's the time for a single crossing. Now, if I want to know if I have a time t available, then the number of crossings is t divided by delta t for a single crossing, or is vt divided by 2r. Okay. And then you see this total change in the squared velocity, the number of crossings times the change in the relative change in the squared velocity per crossing. This is given by vt over 2r 8 over n ln n over 2. And now I use this result to define a so-called relaxation time by saying the relaxation time is the time needed to change the velocity completely. Okay? So I would say I want this to be approximately 1. And then the time that is needed in order to have this change is called relaxation time. And this is given by 2r over vt n divided by ln n over 2. Okay, and since all of our, wait a moment. Let me put it here. And since all our estimates have been relatively crude, what you often see is the same result by dropping the factors of 2 here. T is gone, of course. R over V. You often see this written in this way. That's an estimate for the relaxation time of a star in a stellar system. So what does this tell you? This tells you that the more stars you have, the more time it takes for the star to change its velocity completely, depending on the radius of the stellar system. And if you evaluate this for the Milky Way galaxy, for example, you find a time that is what's the time? Yeah, you find a time that's on the order of 10 to the 7 years. While the universe is about, wait a moment, no, 10 to the 16 years. Look, here are the estimates. Okay, so the upper one is the relaxation time for a star in the galaxy. And you see there, okay, the crossing time is of order 50 million years, like you see here, and the relaxation time is of order 10 to the 16 years. This is much more time than we have available since the Big Bang. Right? The universe is younger than that. The universe is about 10 to the 10 years old. So this means that a single star in our galaxy cannot have changed only a small fraction of its velocity. On the other hand, if you take a globular cluster, right, a stellar system that combines approximately 10 to the 5 stars within a small radius here, then you see that the relaxation time in a globular cluster is on the order of 10 to the 8 years. And globular clusters are among the oldest objects that we have in the universe. So what does this tell you? Of course, right, the whole derivation shows you that we made a number of very crude approximations. Nonetheless, this formula here gives us an estimate for the time it takes for a star to change its velocity completely according to fluctuations in the gravitational field caused by other stars. And there are stellar systems, obviously, that are relevant for astrophysics, in which this time is very, very long, such as the galaxy. And there are others in which this time is very, very short, in comparison to the age of the universe or the age of these respective objects. Okay, this means that if I consider the motion of a star through the galaxy, or a galaxy, let's say, encounters with other stars are essentially irrelevant. What is irrelevant for the motion of the star is its interaction with the entire gravitational potential of the stellar system. However, if you look at a galaxy cluster, collisions between individual stars are obviously very important. Right? And then we do not have, we do have a completely different situation than we have, for example, for a star in a galaxy. Okay, so this estimate tells you that you have to be very, very careful in applying assumptions about stellar systems being collisionless or not. Right? If the relaxation time is very long, where are we? If the relaxation time, according to our estimate here, is very long, then essentially the stars move as if they would not collide with other stars. And then I can consider them moving in a smooth gravitational potential. If the relaxation time is very short, I would have to take into account that stars frequently collide with other stars and change their velocity. Okay, this has profound consequences. Think about a stellar system, for example, that you want to reach equilibrium. In a galaxy cluster, in a globular cluster, the relaxation time is so short that very quickly you thermalize the motion of the stars in that globular cluster. Right? Collisions will lead to velocities changing their direction. And in this way, by these collisions, you will change ordered kinetic energy into unordered kinetic energy. And this means that very quickly the stars in a globular cluster, for example, will behave as if they had a thermal distribution. But this means that then you can assign a finite temperature to the globular cluster. And because of its finite temperature, it will radiate, right? It will throw particles out. It will lose stars. And then it will have to reach a new equilibrium. And the short relaxation time means that it can very quickly reach a new equilibrium. And by the virial theorem, this new equilibrium will mean that the globular cluster will then be a little bit smaller and hotter because of the minus sign in the virial theorem. But if it is hotter, it will radiate more stars. And this would mean that there is no equilibrium state for such objects. Okay? And this is essentially an unsolved problem in stellar dynamics. We do not know whether something like a thermodynamical equilibrium state or a maximum entropy state or something like that would exist for gravitationally bound objects. Okay? Good. It's 10 o'clock, or a little bit less. Please have a look at the quiz on the webpage of the lecture. And then we take about 10 minutes or 15 minutes for you to go through the quiz. And then I will have a better impression of where you are. All right. I hope it's going to be visible. Can you find it? Is it there? Or maybe I should say multiple correct answers are possible. Do you need more time, or are you done? Is there anyone who needs more time? Let's move on then. Thank you very much for doing the quiz. It's important for me to see what the situation is. All right, now, these estimates of relaxation times, crude as they were, right, are very important in order to see what kind of assumptions we can reasonably make about the dynamics of a stellar system as a whole, and which assumptions would apply to which kinds of objects. Now let us consider, or let us focus on situations where the relaxation time is very long. Okay? What does this mean? This means that encounters between individual stars or objects are very rare. Of course, this does not mean that the stars do not interact. They interact through their joint gravitational potential. And the assumption of having no direct collisions between stars essentially means that fluctuations in the gravitational potential are small compared to the overall smooth assumed gravitational potential. All right, now let us focus on systems that are collisionless. So what we are going to restrict ourselves now to are situations in which the relaxation time is very long. And this will lead to what is called the Jeans equation. After James Jeans, has this necessary joke, right, that they are called Jeans equations because Maxwell discovered them. But Jeans applied them to the gravitational situation. Okay, if we can assume a collisionless situation, then of course we return to Liouville's equation. And what does this mean? Then we are considering the entire stellar system as one object characterized by its phase-space density. This is a possibly dangerous assumption already, right? Because obviously the phase-space distribution of a stellar system, considered as a system of point masses, cannot be described as a smooth phase-space distribution. And actually, you should ask, or we should ask, where in phase space is each individual star? And then the phase space density would be a collection of delta distributions, you know, spikes everywhere. And of course, what we are assuming here is now that the scale that we are looking at, or the scales in configuration space and in momentum space, are large enough to include many stars. So that in each subvolume of phase space that we are interested in, there are so many stars that the sum of delta functions that it contains is actually dense enough for us to say that this is a smooth distribution. Okay? There's a whole literature about how to approach this properly. Right? But let us assume that we do have a phase space distribution F. Then we know that dTF plus x dot times gradient x of f plus v dot times gradient v of f equals 0. So remember the possibly far-reaching assumptions that we already made by writing this down. Right? Setting the right-hand side equal to 0 means we must have situations in which the relaxation time is very long. Writing f on the left side already implies that there is an object that we can call f. Right? A differentiable distribution in phase space. All right, given that, we can use that v dot is the gradient minus the gradient of the gravitational potential and write dtf plus x dot times let me write v instead. V times gradient f minus gradient phi times velocity gradient of v equals 0. Okay. Here we make the next implicit assumption, right? We are assuming that there is a joint gravitational potential phi in which the stars are moving. As discussed, right? This is in line with our assumption that the relaxation time is very long. But okay, this is how it is. All right, and now we do essentially the same thing as we did when we spoke about hydrodynamics. Right? We take moments, velocity space moments of this equation. Okay, and we are going to use that. The velocity space integral of the phase space distribution is n. Okay, so this means that we are normalizing the phase space distribution such that the dynamical variable is not the momentum but the velocity. Okay? I'm doing that because otherwise I would have to carry around particle masses here. Okay, then next thing I'm going to do is that, like in hydrodynamics, if I integrate d3v over f times some quantity q, this is going to be n times the average of this quantity q. And what this means is that it's the velocity space average. Okay? All right, I'm going to use these two expressions. And now I'm going to integrate, first of all, the Liouville equation in the last form that is on the board over velocity space. So then, I have expressions like that. Okay. Now, what is this? By definition, that's just a partial time derivative of the spatial number density, dTn. Okay, here I have a derivative with respect to the spatial coordinates, but an integral over the entire velocity space. So I can write this integral as a gradient with respect to x times the velocity space integral over v times the phase space distribution f. And if you take the divergence of this, you see that it's just the gradient of, or it just returns the gradient of f here. Okay, so we have that, and then here we have the configuration space gradient of the gravitational potential. I can take this out of the integral. Then I have an integral remaining over d3v gradient v times f. Now, what is this? I can write this as a divergence term over, as a gradient of, no. What do I have to do here? That's a velocity space gradient. I'm integrating over velocity, so that's a boundary term. There's a boundary term in the phase-space distribution, and I have to carry this out between boundaries at infinity. And I have to cover the entire velocity space here. There, I need to assume that the phase-space distribution f falls down to 0, so this complete expression is going to vanish. And then you see that our equation reads divergence of n times an average velocity, that's the expression here, equals 0. Now, what is this? This is the continuity equation, of course. In other words, stars don't get lost. This is not trivial. It's a consequence of having assumed that there are no collisions. If there had been collisions, you could kick particles out of the system. And then the number density, of course, would not be conserved. So it's not at all trivial here. And it's a consequence of our assumptions here that there are no collision terms. Okay. Good. Next thing we do is multiply this beautiful equation with the velocity and then integrate again over velocity space, exactly as we did for hydrodynamics. All right, so then what do we have? Now we have the velocity space integral of v times dtf. Okay. Then, I have velocity space integral of the velocity times this object here. Let me write this in the following way. It's a tensor product of v times the gradient of f. Right? If I multiply this out, I get exactly what I wanted. Namely, I have a scalar product here through the matrix multiplication, a scalar product between v and the gradient of f. And this is then multiplied with a vector v. But I need this in tensorial form, right? I need to pull out the gradient of f from the entire integral here. Okay, so that would be the next term here. And then we have minus. And now again, I'm going to pull the gradient of the gravitation potential out of the integral. And then I have v times the gradient with respect to v of f. So d3v, v times the gradient v applied to f. This is 0. Okay. What did I do? Right, I multiplied the Liouville equation with the velocity and integrated again over velocity space. So this is moment number 1 of the Liouville equation, moment number 2. Okay, so what is this? I can pull out the time derivative of the integral, and then what remains is dtn times the average of v. Okay. Here, I can write this again as divergence, right? As I pull the gradient out of the integral. And then what remains is, again, an integral over the velocity space times some object times the phase-space distribution. So that's exactly of this type here. And now the quantity is this velocity squared tensor v times v. So this is this object here. N times what is called the velocity dispersion tensor. Okay, now here, look what we do. We do a partial integration, right? This is a velocity space gradient, so I can apply this to the velocity instead. Then I have to change the sign. Then I get this integral here, d3v. Now, the velocity space gradient of the velocity, well, that's the unit matrix times s. Plus boundary terms. But since the boundary is where the phase space density has dropped to 0, they don't add. But then what we have here is just an integral over d3vf times the unit matrix. So this is just the spatial number density times the unit matrix here. This is multiplied with this vector here. So what remains is just n times the gradient. Okay, so let me summarize this again in a little bit different way. We have dtn times v plus the divergence of this object equals minus n times the gradient of phi. Okay, now I'm going to split the velocities exactly as we did on the way to the hydrodynamical equations. Namely, I'm going to say the velocity is an average velocity plus a perturbation plus a fluctuation of the velocity, such that the average of the fluctuation is 0, right, by definition. Then what you see is the average of the velocity squared can be decomposed as the square of the average velocity plus the average of the fluctuation. Okay? And now I'm going to replace the average velocity just by the v symbol here. And I'm going to call this object sigma square. So this is a tensor that characterizes the dispersion of the fluctuations in the velocity, the fluctuations about the mean. Okay. So, if I do this, then I can write the continuity equation as dtn plus the divergence of n times v equals 0. That's the usual way that you know from hydrodynamics, except that the number density there was replaced by the mass density rho. Okay, and the second equation gives me dtnv plus, now, the divergence of n times v tensor v. Now v is the average velocity, right? And we have plus the divergence of n times sigma squared. That's divergence of the fluctuations. And we have the same thing equal to n gradient phi. Okay, now remember what we did in hydrodynamics. We identified terms in the Euler equation that combined to the continuity equation and used that the continuity equation says that the combination of these terms is 0. We can do the exact same thing here by writing this is v times dtn plus the divergence of n times v. But then I have terms left where the time derivative applies to the velocity and v times the gradient applies to the velocity. So then I have plus n times dtv plus n times v gradient applied to v plus divergence of n sigma squared equals minus n gradient phi. Now, of course, the first pair of terms combines to 0 due to the continuity equation. All right, and it's still here. And the rest of the terms can, so we have dtn, just to be complete, dtn plus the divergence of n times v equals 0, and we have dtv plus v times the gradient applied to v. Remember, these two terms that I've now written down are the total time derivative of the velocity. So this is the total acceleration, and you see that this is given by minus 1 over n divergence of n sigma squared minus gradient phi. Okay, so it almost says the trivial thing that stars are accelerated by gravity. Almost. There's an additional term. Remember what we had at the same place in hydrodynamics. In hydrodynamics, we had minus gradient p over rho here. So this means that the velocity dispersion tensor sigma square adopts the role of the pressure in hydrodynamics. And this is the only change. So this set of equations here are called the Jeans equations. Sometimes only the second equation is called the Jeans equation, because the first is taken as granted. All right. Yeah, I mean, first of all, if you compare them to the hydrodynamical equations, you see that the pressure is changed by the velocity dispersion tensor. What is more important is the following consideration. In hydrodynamics, we have started from systems for which we assumed that collisions are infinitely frequent and happen on a very short and ideally negligible length scale. And then we could not set the right-hand side of the Liouville equation to 0, but we could set velocity space integrals of the collision term on the right-hand side to 0. Here, we did something conceptually completely different. We have assumed that there are no collisions at all. And then the right-hand side of the Liouville equation is 0 from the start and not only after changing to velocity space integrals. The resulting equations have exactly the same shape. Therefore, they have exactly the same meaning. But their origin is totally different. Okay? So don't get fooled into that and say, oh, it's the same as hydrodynamics. No, it's conceptually entirely different. But the equations are the same. Why is this the case? Because they are conservation equations and nothing else. Right? Okay. Now, let's do something necessary but completely boring. Sorry for that. Apologies in advance. The point is, we now have to move to spherical coordinates. Okay. Why do we have to do this? Well, because afterwards we are going to look at objects described by spherical polar coordinates. Not necessarily spherically symmetric objects, right? But objects described by spherical polar coordinates, and see what we see in projection. And we have to switch to spherical coordinates. This means we are walking along the way towards what is called the radial Jeans equation. And as you will see, this contains such a lot of unexpected terms that we have to derive this in a very systematic manner. And having to derive this in a very systematic manner means that the derivation will be rather boring. Sorry. We start with the following thing. We say, okay, we have a radial unit vector in spherical polar coordinates. Which looks like that. And it has brothers and sisters, namely E theta equals cosine phi cosine theta, sine phi cosine theta minus sinus theta, and E phi is minus sinus phi plus cosine phi 0. Okay, see, these are the unit vectors in spherical polar coordinates. Nothing new about that, I think. Now, what is the time derivative of the unit vector in radial polar coordinates? Well, first of all, this is theta dot times E theta. If I apply the time derivative to theta. Okay, if I apply the time derivative to phi, I get phi dot sine theta E phi. Okay? If I take the time derivative and apply it to the phi coordinate here, it's going to be 0 here. It's going to change this to minus sine phi, this to plus cosine phi. So if I multiply this with sine theta, I'm there. Okay. E theta dot equals minus theta dot ER. Obviously, right? If I apply the time derivative to the theta coordinate here, this is going to change to minus sine theta. And this is going to change to minus cosine theta, and then I'm here. Okay, fine. And then I get plus phi dot sine theta E phi as before. Cosine theta, sorry. E theta dot cosine phi cosine theta phi dot, yeah, should be correct. Okay, and finally, E phi dot. Now this is what? First of all, this gives me minus phi dot. And then you see I can write this down as sine theta ER plus cosine theta E theta. Okay, let's see. If I take sine theta times this plus cosine theta times this, the sine square plus cosine square just gives me cosine phi in the first component, sine phi in the next. And then I have cosine sine minus sine cosine, which gives me 0 here. Okay, so I get this. Good. Now, if I start with a vector x being r times ER, you see that the velocity can be written as r dot ER plus r ER dot, and ER dot is theta dot E theta plus phi dot sine theta E phi. Okay. And this means that I can write the triple of velocity components in spherical polar coordinates, Vr, V theta, V phi, as r dot, that's the radial component. The theta component is r times theta dot, and the phi component is r phi dot sine theta. Okay? This means I can write ER dot as V theta over R times E theta. Okay. Then phi dot sine phi is V phi divided by R. So this is plus V phi divided by R E phi. Same thing here. I can write this as minus V theta over R times ER plus V phi over R E phi. Sorry. Not so fast. Now I need to change the cosine theta here as well. What I have is phi dot sine theta. What I need is phi dot cosine theta, so I need to multiply this by the cotangent of theta. So this is going to be V phi over R times cotangent theta times E phi. Okay? And here I first have, well, I can just pull the sine theta out. Then I have minus V phi over R. And what is left is ER plus, again, the cotangent of theta times E theta. Okay? Sorry. Because now what we need are the accelerations. So we need this. So this will be Vr dot ER plus V theta dot E theta plus V phi dot E phi. But of course we are not done, because now we get plus Vr times ER dot V theta over R times E theta plus V phi over R times E phi plus V theta minus V theta over R times ER plus V phi over R times cotangent theta times E phi from here. And finally, plus V phi times E phi dot, so minus V phi over R times ER plus cotangent theta times E theta. We need this in order to relate the time derivatives of Vr, V theta, and V phi to the potential gradients. And you see the mess that we have created that way. So this means that we can write the components of the acceleration in radial, theta, and phi directions, which are the minus gradient, negative gradient of the gravitational potential, as Vr dot, I'm just collecting terms proportional to ER now, minus V theta square over R minus V phi square over R. So that's the radial component of the acceleration here. Now I need the theta component of the acceleration, V theta dot, plus Vr times V theta over R minus V phi square over R times cotangent theta. Suppose you would have had to guess these terms. And then finally, the phi acceleration is v phi dot. Now what? VR v phi over r. That's this one, and then we have did I do it? Oh, okay. Plus v phi v theta over r times cotangent theta. Okay. And remember, what we needed in the Liouville equation were the potential gradients. No. What we needed in the Liouville equation were the time derivatives of the velocity components, and we needed to relate them to the potential gradient. So in spherical polar coordinates, this is minus dr phi, comma, d theta over r phi, d phi over r sine theta applied to phi. Okay, so where we simply could write v dot equals minus gradient phi before, we need to write vr dot equals minus dr phi plus these terms, and so on and so forth, right? So what we will have to continue with on Wednesday is the following thing. We need to replace vr dot, v theta dot, v phi dot by minus dr phi minus v theta square plus v phi square divided by r. Then d theta phi divided by r plus vr, v theta divided by r minus v phi square divided by r cotangent theta. And finally, d phi phi divided by r sine theta plus v phi times vr plus v theta cotangent theta divided by r. This is the transformation rule we have to apply. No way around that. So remember, we said that this must be 0 here. So we need all the components of v dot. And this is the reason why we need to express them now correctly in spherical polar coordinates. And since the spherical polar unit vectors are moving over time, all these terms arise here. Okay, so that's the prospect for the first about 10 minutes of next time. And we have to insert this there. And then again, we take one particular velocity moment, namely the radial velocity moment. And then the equation is going to shrink instantly to manageable size. But this is a step we have to go through, because otherwise, if you start from this equation, for example, and say, I'm going to spherical polar coordinates, you're almost certain to lose at least about a third of the terms. This may be correct under certain additional assumptions, but yeah, okay. Good, so much for now. Please, if you haven't filled the survey for the exam, please do so. See you on Wednesday.